Welcome to another session of online course on Inference seminar. Today, we are very excited to have Alberto Abadie from MIT talking to us about synthetic controls for experimental design. We are also very excited to have Dmitry Arkhangelsky from CEMFI as the discussant. Today's Q&A will be handled by Dominic. So without further ado, I pass the mic to him.
Okay, thank you. As usual, please submit your questions via Q&A. Today we have one of the collaborators, Jinglong Zhao, in the chat, so he will answer questions there. Some of them we might also select and ask Alberto directly. Without further ado, let's get going. Alberto, you can start whenever you're ready.
Okay. Okay, you see my screen? Can you see my screen?
Yes.
Yes.
Okay, great. Very good. So thank you so much. Thank you to the organizers, and of course, thank you to Dmitry for, discussing the paper. Today we are going to talk about synthetic controls for experimental design. This is this young work with Jinglong, who is a panelist and will be answering questions from the Q&A. So, many of you may know that the synthetic controls are widely used to estimate treatment effects in observational studies, especially in settings where the treatment is deployed at some aggregate level, so it affects entire cities or regions. What you may not know, or may, but perhaps not, is that synthetic controls are also they also play a key role in experimental design, especially in industry where marketing campaigns may be deployed also at an aggregate level. And so what I'm going to do is I want to start, I should say, this talk by telling you a little story that I guess is going to motivate what we do in this paper. So in my story, we have a ride-sharing company in the US, and what they want to do is they want to assess what will be the impact of increasing incentives for drivers, so giving extra compensation to drivers. And the first way they think about how to evaluate these policies, running a randomized controlled trial or an A/B test. And they will go to a city, and in the city, the drivers will be randomized either to the treatment group, in which they will receive extra compensation, or to the control group, where they will receive the current compensation. But pretty soon they realize that this experiment is going to be problematic, at least for two reasons. First, there will be some type of fairness considerations, because you have in the same city different individuals being paid different amounts of money exactly for the same job, and this is something that the company may want to avoid out of equity concerns, or perhaps because of PR considerations. But even if you don't care about that, there are interference issues in this experiment, right? If drivers that are in the treatment group work longer hours because they have higher incentives, they are going to be still in business from the drivers in the control group, and this will cause a bias in the experimental estimate. So they are going to discard this option, and they go back to the drawing board, and what they realize is wait a second, when we were in grad school, we learned that when there is this type of interference, what we have to do is we have to randomize across perhaps more aggregate units in order to avoid this type of interactions. So they decide that perhaps they want to do a grand experiment in which they are going to randomize the treatment, not across drivers, but they are going to randomize the treatment across cities, and perhaps they are going to assign half of the cities in the country to the treatment group and half of the cities in the country to the control group. But also almost immediately they realize that this is not feasible. First, it is going to be very expensive as an experiment, especially if the treatment results in financial losses for the company. Still is going to raise many equity concerns. You have half of the drivers in the country, about half of the drivers in the country with higher compensation than the other half. These type of experiments that are so large, in some cases they become one-way doors. I mean, you will create much disappointment among the drivers in the treated if the program is rolled back after experimentation, and also depending on how many cities this company is operating in, like the number of cities that you may have, like may not be like large enough for randomization. So plan A discarded and plan B discarded, and they start to think about what they can do instead. And what they come up with is like, okay, we cannot do either of these two things, but we could go to one city and advertise this pilot program and apply it in this city, either in one city or a small number of cities, okay, and see what happens there. And when they decide that they are going to go this way, the first thing that comes to mind is like which cities should be treated, which cities are they going to assign to the treatment group, and which cities they are going to use to reproduce how the treated cities would have done in the absence of the treatment. And what is tempting here, is very tempting, is to randomize, because randomization gives you like a like a pre-assignment, you have like an unbiasedness, but then you realize that, randomization in a case in which you have one or two treated units may create very defective designs in which the treated cities are not representative of the entire set of cities in the countries, or the treated cities are very different from the control cities. Okay, so what we are going to do in this presentation, we're going to talk about using synthetic controls for experimental designs, and it's going to be like a non-randomized experiment. It's going to be an interventional study, therefore an experiment, but we are not going to randomize. What we are going to do is we are going to choose like treated cities and control cities in our experiments to attain some balance in the characteristics of the predictors of the outcome variables. Okay, so the choice of the treated unit, we will try to accomplish two goals. The first goal is that the features of this treated unit are representative of some aggregate of interest, like the entire country. And also the other thing that we want to do is that the treated units are not idiosyncratic in a sense that they cannot be, their characteristics cannot be reproduced by a set of untreated units. And these two goals are not typically intentional. Okay, so you will see that in contrast to the observational case for synthetic controls, in which the treated unit is given to us, here we have to choose both the treated unit and the control unit. So we're going to have a synthetic treated unit, we are going to have a synthetic control unit. And one of the fun things about giving this talk is that with very, very high probability, like all of you have been a subject in one of these experiments, the type of experiments that I am going to describe. They are very much used for geoexperimentations in for example, the companies that I have here in the slides, but may also many other companies in the tech industry. And and although these methods are very much used, in practice, the academic literature on synthetic controls for experimental design is really starting. There are not that many papers. I want to highlight here a work by Dochenko, Hideo and co-authors, and also there is some work out there by Jones and Barrows from Uber that has motivated the example that I was giving to you earlier. Okay, very good. So let's start with some notation and concepts. We are going to work with a panel. We're going to have T time periods and J units. The units can be cities in the ride-sharing company example. We're going to have a T0 pre-experimental period and T1 experimental period. So this means that at T0, there is an analyst sitting there trying to think about which units are going to be selected for treatment and which units are going to be selected for the control group. And the treated units are going to be treated over the entire set of experimental periods. We are going to operate in a setting with potential outcomes. We'll have the two potential outcomes, Y IJT and Y NIJT. These are the potential outcomes for unit J at time T with and without the treatment. And the treatment effects are going to be defined as usual as the difference between these between these two potential outcomes. Okay. And what we observe that is the outcome of interest, also as usual, is going to be the potential outcome with treatment for the treated unit, the potential outcome without treatment for the untreated units. Okay, and what we are trying to estimate. So we're trying to estimate some average treatment effect in this population of J cities. We have it here. Okay, and these weights have we're going to assume that we know them, or we can estimate them previously, like in the simplest and perhaps most common case, F maybe 1/J, capital J's, then we have uniform weights. But in other cases, they may be related to the size of the population in the city or the size of the market in that city. Okay, and in a synthetic control experiment, what the experimenter is going to do is going to choose two sets of weights. It's going to choose the set of weights W, and it's going to choose the set of weights V. And both of these weights, they are going to be like a vector with J entries, one entry for each of the units in the sample. Okay, and the weights are going to be they're going to be non-negative. They're going to sum to 1, and each unit can contribute to one of these vectors, but not to both of them. So the idea is that you will see in a moment, each unit can contribute to the synthetic treated, or can contribute to the synthetic control, but cannot contribute to both of them. Okay, so how are we going to interpret these weights? I was starting to tell you about this. So we are going to say that, or we are going to interpret units with a weight W that is bigger than 0. Those are the units that will be assigned to the intervention of interest in the experimental periods. Okay, and units with W equal to 0, they are going to be our donor pool of untreated units, and from this donor pool we can choose the one that are going to contribute to the synthetic controls, and the one that are going to contribute to the synthetic controls are going to have positive V weights. Okay, so imagine that I give you a W and I give you a V, and how do you get a synthetic control estimator in this setting? This is going to be very easy. What you are going to do is you are going to take the average outcome for the synthetic treated unit minus the average outcome for the synthetic control unit, and this is going to be your estimator. Okay, so that's if I give you the W and I give you the V, but you can think about, okay, so there are many possibilities for these weights. So how I'm going to choose, how I'm going to make my choices W star, V star. Okay, so let's go to that. So if the experimenter is having, a really good day, the experimenter would like to attain that, would like to have, I'm going to have, the average, a outcome for the synthetic treated unit, and I would like that this average outcome for the synthetic treated unit is the same as the average outcome with the treatment in the population for the post-intervention period. So that will be goal number 1. Okay. The second goal of the experimenter is about choosing the V's. Is you can think about it in 2 possible ways. The first one is very similar to 1. It's okay, so let's take the average outcome for the synthetic control. I would like that is the same as the average outcome for the average outcome without the treatment. In the population. So that would be also nice. But an alternative is the following. Perhaps we want to choose the average outcome of the synthetic control such that it reproduces the average outcome of the treated for the treated without the intervention, W weighted. So we have a 1 and 2 or 3. So we are going to see that either we want these 2 or we want this one. Okay, why? Because if we have 1 and 2, an experimenter could operate in this way would the estimate will be exactly the same as the average effect of the treatment in the population. And if you cannot do 1 and 2, but you can do 3, then you will get the average effect of the treatment on the treated W weighted. That is the parameter that is studied in the paper by Dotchenko and co-authors. Okay. It would be great if we could do that, but of course we cannot directly fit potential outcomes because they are not directly observed. But instead, what we are going to do is we are going to fit the predictors of these potential outcomes. Okay, so how are we going to do that? First, we are going to define some fitting periods. So what are these fitting periods? These are going to be like they're going to be a subset of the pre-experimental periods. So like we're going to have like TE of them. Okay, and from the point of view of estimation, you will see that we could take the fitting periods the same as the entire set of pre-experimental periods. But you will see that there is like it is advantageous for us to leave some pre-experimental periods aside to use later for inference. Okay, so the first thing that we are going to do is like we are going to put the outcomes of the units in the fitting periods. We are going to put them in this vector y, e, j. Okay, and next what we are going to do, we are going to construct this vector of predictors that is going to be the outcomes of the pre-intervention outcomes during the fitting periods, and also like any other predictors that we might take in consideration, like a size of a city or something like that. Okay, and the next thing that we are going to do is like we are going to calculate what is the average of these predictors for the entire population. Okay, this is the population average that you'll see in a moment. We will try to reproduce with our synthetic control. Okay, so now that we have all these elements in place, how are we going to choose synthetic controls? There are many alternatives, we talk about many of them in the paper. Here we are I will go over only a couple of them. This is perhaps the most, this is the most basic of the formulations that we have in the paper, that we operate here in the following way. So like we are going to choose a synthetic treated unit that is going to reproduce the characteristics of the predictors, the average of the predictors in the population. And we are going to choose a synthetic control unit that is also going to reproduce this average, of the predictors in the population. This is, given to us the restriction that we are going to have on the weights. And finally, we have here a cardinality restriction. It says that, perhaps like you are going to have you're going to be limited in the number of units that you can treat. So like you're only going to allow yourself to treat like n bar units. Perhaps n bar is equal to 1, is equal to 2, is equal to 3, and perhaps you also have like a minimum number of units that you can treat. Okay, you could replace this with a more usual like a linear budget constraint, but for simplicity, I'm going to leave it like this. And if you look at this problem, you will notice very, very fast that the problem is almost symmetric in the W's and the V's, except for the last constraint. So if the last constraint not only holds for W but also holds for V, you could swap the weights. Okay, you could make the W weights equal to the V weights and the V weights equal to the W weights. And we talk in the paper about how to decide between all these swaps. Okay, very good. So this is kind of the most basic version of the synthetic control estimator for experimental design. As I said before, we have like a lot of variations in the paper, and whether you want to use one of these variations depends on what you are trying to attain. Okay, let me tell you about one of them. So here we have a setting in which the synthetic treated unit is like trying to reproduce the average of the predictors in the population. But the synthetic control unit is doing something different. For the synthetic control unit, we are taking the predictor for each of the units that contribute to the synthetic treated unit, and then for each of these units we are fitting a synthetic control. Okay, and we are going to have like a different synthetic control weights for each of the treated units, and then we are going to aggregate all these weights to get our synthetic control. And this xi is like going to moderate the trade-off between fitting well what happens in the population, and having like a targeting something the average effect of the treatment on the population, or fitting well on the treated units and having like a good estimate of the average effect of the treatment on the treated that is W weight. Okay, so this is this type of formulation allows you to make these choices. Something else that you may want to do is like you may want to cluster your observations in the space of the predictors before doing any of these methods, right? Like here we have the reason, like an example that illustrates why you want to do this. So like both, the dots in panel A and panel B are, exactly the same. They represent, the space of the predictors. Imagine that you have only 2 predictors, and imagine that you are going to assign like 3 units to treatment. And if you do like some of the, some of them, designs that we have in the paper, you may end up with the 3 treated units that are the red ones here in the middle of the distribution. But of course, when you look at this example visually, this is not what you want to do. What you want to do is like you want to cluster your observation, these 3 clear clusters, and assign one of the treatment units to the cluster. And that's another setting that we consider in the paper. Okay. So what are the properties of synthetic control estimators? In order to figure out the properties, I'm going to adopt a benchmark model for the a data generating process for the potential outcomes. This is not the only possibility, but is one that is has been considered in the literature quite frequently. We are going to think that perhaps the potential outcome without the treatment is produced by a factor model, and in this factor model you have characteristics of the units that you observe, characteristics of the units that you don't observe, and they enter the model with a coefficient that can vary arbitrarily with time. Okay, and then you have like some individual transitory shocks. And if you go to papers that look at the synthetic controls for in observational study, you will see a model like this. You will not see the second one. The second one is for the potential outcome with treatment. The thing is that in models with in observational study, we are already given the treated unit, so like we don't need to say anything about the potential outcome with the treatment. But here we are going to choose both the treated unit and the control units. Okay. So what can I say again? What can we say about the estimation properties? Like, well, this is part of what we can say first. If imagine that you are able to fit the characteristics of the average in the population for both the C's and the Y's, and you do it both with the treated unit, the synthetic treated and the synthetic control. Okay. Then under these conditions, you can establish a bound on the bias of the synthetic control estimator, and this bound is going to depend on this ratio here, when sigma bar square is the variance proxy of epsilon xi's that are sub-Gaussian under our assumptions, and then in the denominator you have the square root of the number of fitting periods. So what is this about, and why we have this this bound? Okay, it would be great if we have like synthetic control units that reproduce not only the characteristics C that are observed, but they reproduce the characteristics mu that are not observed. Okay, so the characteristics C we can fit directly because we observe them. The mu we cannot fit directly, we don't observe them, but we can use proxies like the outcomes. We can use the outcomes as proxy to fit mu. Okay, and if our fitting of the outcomes comes from implicitly fitting the mu, we are going to have a very low bias. But if our fitting of the outcome comes from a fitting out of the epsilon xi's, then we are going to say that we have overfitting. Okay, and the risk of overfitting is going to increase when there is a lot of variability in these errors, and it's going to also increase when you have like a small number of pre-intervention periods. So that's the intuition for this result. Okay, something that I wanted to mention is that you don't need to fit the predictors exactly, like you may and you will in most cases like have some error in fitting these predictors, and that's going to add like a constant to the bias of the estimator. Okay, so this is what we know in terms of the properties of these estimators. We know that if we have series that are smooth in terms of the variance of the epsilon xi's are is relatively small, and we get this by aggregation because we are thinking about aggregate units, and we are able to fit this, this predictor for a, large number of pre-intervention periods. We know that we are going to have like a small bias. Okay, how can we, do inference in this setting? Like, let me talk about a couple of alternatives here. One of this is like trying to, test some null hypothesis. Now, a null hypothesis here is that, this set of coefficients, they are going to be the same across equations, and then these two variables, these two shocks are going to have the same distribution. And if that is the case, then under this hypothesis, the distribution of the potential outcome with the treatment and without the treatment, they will have exactly the same distribution, although they have may have different relations, of course. And this is where, using the blank periods is going to be useful for us, because what we can do now is we can, estimate placebo effects over all these blank periods, and we can, construct this vector R hat that is going to be, all our estimators in the in the experimental periods and all our placebo, estimated treatment effects. So this is like a, a long vector, and from this long vector we are going to have like a T1 combination. Remember, T1 is the number of experimental periods. So we are going to take from this vector like a T1 elements, and we are going to put in some vector E pi hat, and we are going to plug in this in some type of a test statistics. Here we have the mean absolute error, and our p-value is going to measure the how many times when we plug these errors of this combination into the test statistic, we obtain a value of the test statistic that is bigger than the value that we use only the estimates for the a post intervention period. Okay, so what are the guarantees that we can obtain on this? That depends on which assumptions you are willing to make. If you assume that the lambda t's are exchangeable, between the blank periods and the post-intervention periods, you obtain a very nice result in terms of the validity of the p value that you are obtaining. Even if the lambda t's are not exchangeable, remember the lambda t's is what multiply mu j's, the unobserved characteristics of the individuals. Then even first, let me go here. Even if they are not exchangeable, this type of result will hold with large probability for large T when you have many fitting periods. And one of the nice thing about this result is even if you have this lambda T exchangeable, this doesn't mean that the Y's and the Y's the potential outcomes are going to be exchangeable. In fact, they can be non-stationary through the term delta T plus tau T times C J. So they may show trends and complicated seasonality patterns, something that the previous results in the literature didn't allow. The previous result in the literature restricted the Y's to be IID in the absence of the treatment. So that's something nice. So something that we can do in terms of inference, if you want to do things in a different way, imagine that you are willing to assume that the treatment doesn't affect the distribution of the individual transitory shocks, epsilon and xi. And in that case, you can use the distribution of the placebo effects in the blank periods to construct confidence intervals for the treatment effects. And you can see that these confidence intervals are valid as long as the number of fitting periods and the number of blank periods is large enough. So this is something that we are going to do later in our simulations and in the empirical application that I'm going to discuss now. So we are going to look here as panel data, store level data from Walmart. We have 45 stores, 143 weeks, and we are going to have the first 100 periods are going to be the fitting periods. Then we are going to have 28 weeks as a blank period, and then we're going to have 15 experimental periods, and we are going to use like a uniform weights in order to define an average treatment effects. And what you see here is like is sales, like in all these stores, these 45 stores through time during the fitting periods and the blank periods. Remember, like our analysis is sitting here and thinking about which units are going to contribute to the experimental treated and which units are going to contribute to the experimental control. And if you run our, like our estimators in this data set, this is what you obtain. You obtain like a synthetic treated unit and a synthetic control unit, and you can see that they follow each other very, very well. They also follow the market. Okay, and you can see why, like in certain, times during this, fitting period, you may have like higher sales because, it's a, like a winter holiday or things like that, you may have higher sales than in other weeks. And this is, the synthetic control is reproducing this perfectly. It's not giving you like any, like a effect during the blank periods. Remember that, we don't use the blank periods to fit the synthetic treated and the synthetic control. And also it's not giving you any effect during the experimental period. And this is great because this is a placebo intervention. There is no intervention at that week. We are trying to estimate at 0. And we say that we see that we estimate at 0. Okay, so this is the, the estimated, placebo effects, you could say during the fitting periods and the blank periods, and you can see that, the distribution doesn't change much during the, experimental period. We have a, p-value that is quite large, and we have like, confidence intervals that cover 0. Okay, so this is for the empirical example. What we can say in terms of a simulation, here is an easy simulation. We're going to have 15 units, 30 periods in total, like 25 pre-intervention periods and 5, like experimental periods. The first 20 periods are going to be our fitting periods, okay? And so what do we do? What do we have here? So this is the result of our random simulation. You see that we have like a very good fit in the fitting periods. It's perhaps not surprising, we are fitting there, but also very good fit in the blank periods. And we have like not good fit in the experimental period because there is a treatment effect in this simulation. And this is the result only just one random draw from this simulation. And if you can see what's going on here, you can see that there is a very little action in the blank periods, but because of the treatment effect, there is a lot of action in the experimental periods, and we reject the null hypothesis of a no treatment. Okay, in terms of what happens across many simulations, so here like we have the values of the treatment effect in the population for the 5 experimental periods, and we have like our estimators. That is, this is the unconstrained case in which we can use any number of a treated unit to calculate the synthetic treated, and this is the constraint case in which here we are only using 1 unit for the treated, only 2 units are treated, only 3 units are treated, and so on. Okay, so like not very surprisingly in terms of mean absolute error, like we do better. The more units that we can use, we do better. But it's still doing quite well with a very limited number of treated units. If we go to a setting, so this is a setting in which there is no treatment effect. So like we have done the same simulations now, but under the null hypothesis. So like you can see that the treatment effects, like you have some retentions that are like big, different than 0 in the simulation, but stochastically they are centered at 0, so there shouldn't be much action. And this is exactly what you are estimating here. You see very small estimated treatment effects, both in the unconstrained case, in case that we can use as many treated units as you want, but also like in the constrained case. And the other thing that you can see here, is like the the distribution of the p-value is basically what you want it to be, right? That this p-value takes value less than 0.05 with a probability very close to very close to 0.5. Okay. What else? So this is interesting because this next table, because you could think about, okay, here the one possibility is to run a synthetic control study of the type that you have been describing during this talk, but there are like other possibilities and why we shouldn't, like do something else. And one of possibilities like randomization. I know that, ex ante randomization is going to give me an unbiased estimator, like even if I only use one treated unit, but like you will be concerned that suppose the estimator is going to be perhaps very much biased because the characteristics of this treated unit may be very different than the characteristics of the units in the population. Okay, so what we're doing here is like we are showing, the results in terms of a root mean square error for, like 1 treated, 2 treated, 3 treated units, and so on, for like using that synthetic control design, and also like using randomization and using stratification. Okay, you can see that we are really improving quite a lot. In terms of, like a root mean square error, like I could show you the same with a mean absolute error, right? These same type of results. There are like a lot that you can gain from not randomizing like a, get you a lot of, defective designs in this type of setting, and may not be exactly what you want to do. Like a comment that we have often is like why don't you stratify? You could stratify this stuff, and you can do that for sure. But I noticed that when we have only one treated unit, these two scenarios are going to be exactly the same, because then you have only one stratum, because like for each of the strata you need to choose one treated unit. So when you have one treated unit, like stratification is not going to be different than randomization by definition, and it can be different when you have more than one units, but what we have seen is that in fact it doesn't improve much, and sometimes like in our simulation, like it decreases the performance of randomization. The other thing that you could do is you could do like a post-randomization adjustment, perhaps using regression. I don't have the results here, but the results that we have so far, they are not very, very promising. In fact, they are quite bad in terms of the effectiveness of post-randomization adjustment. And perhaps the reason is that, like here we have very, very few units. Like in this simulation, for example, we have only 15 units, and we may have a large number of covariates. So like this type of adjustment may be difficult to carry on. Okay, so let me just stop there with a couple of slides, like with some final thoughts. We tend to think about experiments as like in experiments. Of course, we randomize. That's what we do in experiments. Experiments involve randomization. This is something that it may not always be the best thing to do. An experimental study is an interventional study, and a study in which we intervene in nature, and we may intervene by randomization, or may not intervene by randomization. You may think about some of the most famous experiments in the history of humankind, and typically don't involve randomization, like William Herschel discovery of the infrared, or something like that, right? But sometimes you can intervene to learn about nature without randomization, especially in the cases in which the number of experimental units is small, is something that you may consider. However, like we know that experimental design methods are very, very effective in many cases. If you focus on large samples, randomization has proven to be great, an enormous success. In my field, economics, but also in many other fields. Our point here is that in many other settings, it's going to become inadequate because treating more than a few units is infeasible, and because we are in a case in which we are trying to treat aggregate units, and this is important because at least in economics, many of the treatment that we care about, we don't we don't deploy them at that individual level. We deploy them at a very aggregate level. There is some regulation, that the regulation happens at the level of a city or a state or a country, something like that. And we want to know what is the effect of this regulation. Okay, so, and in experimental settings, as I said before, also you may have like some, like a treatment that may only be, deployed at an aggregate level. So the synthetic control design that I've been discussing, optimizes jointly over the identities of the units that will be assigned to the treatment and the one that will be assigned to the control group, and also over the weights that these units are going to contribute to the synthetic treat and the synthetic control. And as I said before, there are many cases in corporate research and academic investigation in which you cannot do interventions at the level of the micro units because they are, we say here, unfeasible, unethical, impractical, or ineffective. Okay, and so I hope that I convey the notion that there is a lot of possibilities to use this type of estimators in in empirical research, and also I think there is a large opportunity to develop methods for this type of empirical strategies, because as I said before, although these methods are very much applied in practice, the academic literature is is still relatively small, so there is a lot of open field before us. Okay, thank you very much.
Thank you, Alberto, for your nice talk. There were a few questions, but Jinglong has already been answering them. So I asked the participants if there are more questions, please write them down in the Q&A. But for now, maybe we can move on with Dimitri's discussion. Dmitry, please take it away.
All right, let me share. So I guess Alberto needs to stop sharing.
Yeah, I need to stop sharing.
Okay, so now I can share. Okay, so thank you very much for the opportunity to discuss this paper. My name is Dmitry, I'm from CEMFI in Madrid. So what is going on? So first I'm going to summarize a little bit, although Alberto just did perfect summary. So I'm an economist, and this idea that often we can only treat units at some aggregate level, be that a market or geographic level like a state, this is super common, right? So this can happen for legal reasons. We cannot just have differential pricing, maybe for practical reasons because it's very costly, or economic reasons, identification reasons, like general equilibrium effects. So the premise that randomization or intervention has to happen at some aggregate level, I think, is very, very common in applications. And by nature of this process, once you go to that level, the number of units that you have is unavoidably small. You cannot have many states. You cannot have many markets. If you start having them, then probably you are starting running into the same problems that led to the idea that you need to do at aggregate level. Okay, so there is a natural constraint here, and we kind of know that if you're in these types of situations, then if you just randomize, and randomization is great, you have an ex-ante guarantee, statistical guarantee, such as unbiasedness or even inference. But because the number of units is small, this guarantee can be potentially useless. Okay, so my favorite example actually from the survey sampling literature is from Basu, who discusses he has an essay on how you wear an elephant in a circus, and it's very much about that. So if you don't know that, I suggest to read it. But kind of clearly, once you are there, you would want to split units into groups carefully rather than randomly, okay? And how do you do that? Well, it's very natural to minimize imbalance in observables and hope that it minimizes the imbalance in unobservables as well. And so what the paper does, I think very nicely, proposes multiple procedures that would work for that purpose in a large class of models using synthetic control ideas to construct groups, right? That's fundamentally what is going on. Now, in terms of underlying models, the simplest case that I can come up with is to write this very simple model where you have the potential outcomes for the treated units that follow just a two-way model. So there is a unit-specific treatment effect, not unit-specific intercept, and then there is a common trend, so then there is noise, and then the treated outcomes follow the same process, but now this unit-specific intercept is multiplied by an additional shock. Okay, and so in this simple model, if I were to look at any sort of weighted average treatment effect, so my weights are gamma I, then what it would be equal to, it would be equal to, of course, this difference in the aggregate shocks that we have here. Also, this the intervention makes this beta appear, so we also have it here, and this this average. Okay, so when we're trying to come up with the right split, our goal fundamentally is to match this average. Okay, so so that when we estimate later, we get the right answer. And the beauty of this setup is that you can do this by observing only control pretreatment outcomes. Okay, so this is something that is kind of key. That it's important that you can do this only by seeing, only by looking at these outcomes, right? So how do you do it? You split the units into groups with appropriate alphas. Okay, so once you've done that, you know that you guaranteed that these terms will match. Now, you don't observe alphas, of course, because you observe y's, but the observed outcomes serve as signals about the unobserved alphas. Okay, so that's the logic, and that helps you very much. That's how I understand what's going on. Okay, and so then there are multiple ways how you can do it, and there are multiple procedures discussed in the paper. Alberto talked about some of them. There are more in the paper, which I think are very interesting. I invite everybody to look at them in detail. Now, in terms of discussion, how I was thinking about, I was trying to connect what I was seeing to still some sort of notion of underlying experiment. I understand that Alberto's point was we might not want to do an experiment because it's impractical, but maybe we can still interpret what we are doing as some sort of experiment. And so the way I was thinking about it is that if I think about the assignment, so WI is this binary indicator, whether you are in the treated group or in the control group, then of course it's a deterministic function of the data, right? So you give me the pretreatment data, and I give you the assignment vector, right? Why? Because it just solves the optimization problem. But at the same time, I can also think of the expectation of this W, where I treat things that are random, right? Like this epsilons here as random variables, and I kind of resolve this problem again and again. And then for each unit, I will have not necessarily a single value, whether this unit is treated or not, but potentially probability, right? So some units might always end up being in the treatment group, but some might somehow end up in other groups. So we can, in principle, think that there is some sort of underlying experiment with an unknown and unit-specific propensity score and potentially very dependent assignment, right? Because maybe all of the units are always together and so on. So the assignment, the underlying assignment can be quite complicated. And so once we start thinking about it that way, it feels to me that potentially, although I'm not sure, the assumption that kind of drives some of the results is the independence of these errors. And I think that can be important, right? Because in these types of experiments, kind of your assignment is going to be related to those past errors, right? And so if those errors are correlated with post-treatment errors, I'm not sure whether you're going to have necessarily unbiased estimator or not, or kind of approximate unbiased estimator or not. I think it kind of depends. Of course, in the regime that the authors consider, they do, but I just I don't know whether this can be easily generalized to arbitrary processes. Although the synthetic control literature, which often assumes explicitly that the assignment is independent of the past errors, right? Which is not true in this in this paper, right? By construction, it does depend on the past outcomes and thus on the past errors. So that literature assumes that here it doesn't hold, but this might not be a problem, right? So we have work with David Hirschberg that kind of shows that in very different setup, but still it might be not a big deal that your treatment assignment depends on the past errors. Okay, so I don't know whether this is an issue or not, but I think the fact that people were doing this, making this assumption typically in synthetic control literature is a little bit different. It's a little bit different assumption. It plays a little bit different role there than here. So I think this is something that is worth emphasizing. Now, the second thing that I was thinking about once I started to think through these terms of underlying propensity scores and everything was to think, can we potentially do maybe better or maybe a little bit differently? And I have no idea whether it would work or not, but let me just propose something. So suppose that I start with the observed data, start with the observed pretreatment data, and rather than just using it to solve the optimization problem, I first feed a parametric panel data model to this data. This can be a panel data model that follows the same structure, like a linear factor model that Alberto was describing, or some other model. I just feed it to the data. It's a parametric model, meaning I can generate data from that model, and I'm just going to simulate data from that model and solve the optimization problems. Okay, the same optimization problem that Alberto is using right now. So when I'm doing that, I'm gonna kind of learn these probabilities that I was describing here as functions of the parameters of my model. And I'm also gonna learn the whole assignment process. So I know which units are gonna be kind of treated together or not. And then I can assign assign units using this assignment protocol that I just learned. And I think that this type of procedure would have a very similar behavior to the one that authors propose, and if my model is good, right? So fundamentally, it has to, right? So if I'm generating the data that looks very similar to what is what we're seeing, then my solutions are going to look very similar. But at the same time, I potentially will have an experimental guarantee, right? Because now I actually am assigning units in an experiment, and I can check how that experiment looks like, how much overlap there is in that experiment. And then potentially I can use it for inference, just that experiment. When I was thinking about it, I was thinking that to some extent this resembles bagging, right? So bootstrap aggregation. Once you look at the problems that Alberto was describing, they have this discreteness in them, right? So which means that potentially you might be benefiting from these types of aggregation, right? So we know that logic from decision trees and then to random forest. So maybe just doing something like that, even if it's not necessarily for different type of inference, but just for as a solution, this can have better statistical performance. Although, I have no idea whether it's going to be exactly the case, but it's just a thought. Okay. Now, going forward, I think that using observed data to construct assignment is very natural in challenging environments, especially in situations when the number of units are small. I think this idea that how exactly we can do that using the panel data models is very natural, and I think it can be pushed more. Okay, so the author is focused on this particular panel data model for which synthetic control type of procedure works well, but there might be other panel data models for which procedures would need to be changed, or we can follow, for example, these ideas that I was discussing in the previous slide. And in general, canonical literature offers many models, right, that one can consider here, and so maybe it's worth exploring what those models, other than the linear factor model, would imply for the similar type of problem. And so then there is also a natural inference question. So for inference, should we use the panel data model, the underlying assumption of the panel data model, which to some extent the authors do, right, when they assume this exchangeability or properties of the errors? Or if I can interpret this whole thing as an experiment, can I rely on the experimental inference? Or maybe I can combine these two ideas together. For example, if I did my simulation and I saw that the propensity scores that I tend to get are very extreme, so most of the units are always in the treated group, most of the units are in the control group with probability 0 and 1, then clearly I cannot do randomization inference, and so I have to use model-based inference. But if I see that there is something more optimistic there, then maybe I can start using a randomization inference. So to me, that's kind of a question. Can we combine these two things? So overall, that's all I wanted to say. I think this is a great paper, very interesting reading, and I know that in practice it's used a lot, even though it might not be used so much in econ still, in academic econ. Thank you.
Thanks for a nice discussion. Alberto, do you want to respond?
Oh, yes. Thank you. Thank you, Dmitry. Thank you for the nice discussion. Okay, let me collect my thoughts a little bit. I think like you're right in everything you say. Like clearly, W depends on the errors, and this has like at least two implications, right? One is like it's generating the bias that we're trying to control. And so that dependence shows up in the bias. If the W's were not dependent on the epsilons, we will not have this bias, and this is something that we're trying to deal with. The other thing I think that you have in mind is that there may be like a time series correlation in the epsilons on the X size, and this may like introduce some biases. That is true. Like we found that this is typically not a big concern, because like you will need to have this correlation to be very, very large in order to like create substantial biases. If you have such a thing, either you can model this correlation on allow some periods to pass before like you do estimation for that correlation to die down. I think that's something like I think that you obtained some similar result in your paper, if I remember correctly. So that is right. But yes, totally, I agree. And you also talk about fitting a parametric model and or something like that, and doing inference. So this reminds me like one like in the YASA paper that was published in 2010. Like we have kind of the same or a very, very similar idea, perhaps like to do inference. Perhaps we can fit all these series and do some type of a parametric bootstrap and so on, and to do inference. At the end we decided not to go in this way because we wanted to have it's totally reasonable. The reason why we didn't go this way is because we wanted to have a procedure that is relatively simple and with not so many researcher degrees of freedoms and so on. But again, it's something that you could do. Like it would be totally reasonable to do that. You also mentioned about the randomization and whether do randomization randomization inference only or based on the or based on the properties of the data generating process, or combine the two of them. So those are also like a very, very interesting thoughts. I mean, like the type of inference that we do, it's not directly like leveraging the model, but they were thinking like if we have this model, we could do this. Like we can think about the properties of that. This permutation or combination type of inference. But you could definitely change the model. And the factor model is kind of natural for synthetic controls because synthetic controls are based on co-movement, and the factor model gives you that co-movement. But there are other models like BAR models or something like that, for which in fact we are going to have better results if we try to do that way. I am not sure. I will have to think a little bit more about this. I am not sure about doing only randomization inference, because no matter what is the propensity score that you get, you are still going to have the same issue, right? That ex ante you are doing great, and ex post is not clear if you are doing great or not. But I am all in favor of trying to combine ideas in the synthetic control literature. I think like you have done, in fact, and other people have done like a kind of a bias correction or augmentation and so on. Like using a model to kill biases of synthetic controls estimators, and that's something that this type of combination could be extended to synthetic control designs, I think. So thank you. Good points, all of them. Thanks a lot.
Thank you. Thank you.
Thank you so much. There are no more active questions in the Q&A. So once again, I thank Alberto, Dmitry, and Jinglong for their participations. And let me just wrap up quickly by sharing the information about next week's seminar. So for next week, we will have the man, the myth, the legend, and one of our founding fathers, Guido Imbens from Stanford University, talking about identification of non-parametric factor models for average treatment effects. Hope to see you all next week. Thank you.